So I wanted to share one of the ways that I think about equilibrium and how it's connected both with this equilibrium constant K, where that actually arises from, and how equilibrium is connected to the ideas of entropy, disorder that we've already talked about. The easiest way I know how to do this is to actually simulate an equilibrium situation rather than to just talk about it in the abstract. So if we were in class, what I would be doing is have everyone be molecules that can undergo a chemical reaction. And because this is a process based on probability, you'd be rolling dice in order to determine whether you react or not. In the absence of a room full of people that I can distribute dice to and we can reenact this, what I have done is I've taken an Excel spreadsheet and used it to simulate a chemical reaction process, much like I would do in class. So here's what I would do. Imagine I have 20 molecules or 20 people in a class, each of whom is pretending to be a molecule, and I have a chemical reaction. A turns into B. And A turning into B doesn't happen all at once. It happens over a period of time, like any chemical reaction does. So my rule for reenacting this reaction, A goes to B, is that for each roll of the dice, and everyone in the class gets to roll the dice, if you roll a 1 or a 2 and you're an A, you get to convert to a B in that dice roll. Think of it as 1 second or 1 millisecond or 1 femtosecond, however slow or fast you want your reaction to be. So here's what we have. We start out with everyone as molecule A. Everybody gets to roll their dice. Different people get different numbers, and these are acted. And after the first dice roll, some folks have rolled a 1 or a 2 and get to convert to Bs. Now we know how dice work. There's 6 different sides, so a roll of 1 or a 2, you have a 1/3 chance of getting that. And about 1/3 of the A molecules will convert to B molecules on the first roll. Second roll follows the same rules. Everyone rolls the dice. Now, if you're a B, it doesn't matter what you rolled, you stay a B. But if you're an A, you get to follow this rule that if you roll a 1 or a 2, you get to convert to a B. So what happens on the second roll? Here's an A that rolled a 1 and gets to convert to being a B. Here's another A that rolled a 1. Here's an A that rolled a 2 and converts to being a B. So we convert over about another 1/3 of our A's. And in the third dice roll, it happens again. Some more A's get to be converted into being B's. The next dice roll happens again. Dice roll after that, we go, here's an A that turns into B, and after a few dice rolls, we get almost everybody has turned into A's, except for this or everybody has turned into B's, except for this one right here. But we know that if we keep rolling, eventually, even this one will turn into a B. This is exactly what we expect from this rule. So we can graph what we had here. How many A's we have as a function of time, each roll, how many B's we have as a function of time. And this does pretty much what we expected. After the first roll, 1/3 of the A's convert. After the next roll, around 1/3 convert. Another third in each successive roll. And we know that eventually A here would be dropping down to 0. B here would be rising all the way up to all 20 being converted. So this is a probabilistic simulation of a chemical reaction. But it's not a very realistic simulation, because what we have neglected here is the reality that every process in the universe can, in principle, be reversed. So if we're going to represent reality, we need a rule not just that A can convert to B, but we need a rule that B can convert back to A. Luckily, I have another spreadsheet here. So here's our second experiment, our second simulation. We keep that same first rule. A can convert to B if an A rolls a 1 or a 2, but now I've introduced a new rule. A B can convert to an A if that B rolls a 5 or a 6. So let's see what happens. We're going to start out with everyone being A's, and everyone gets to roll the dice. Lo and behold, some A's roll 1 or 2, they convert to being B's. This is a lot like our first step from the last simulation, because there's no way to apply the second rule. But on the second roll, we can now have both rules in play. On the second dice roll, we can have A's that roll a 1 or a 2 like this one and convert into being B's. We can also have B's that were formed in the first dice roll that roll a 5 or a 6 and convert back to being A's. So you can actually see we get a lot of conversion from A's to B's on the first roll, but in the second roll, well, when we sum them up at the bottom after the second roll, we actually have the same number of A's and B's after that second roll, because some A's have converted to B's, same number of B's have converted back to A's. Same idea is true in the third dice roll. Some A's, like this one, are going to convert to B's. Some B's are going to roll 5 or 6 and convert to A's. And in this case, those numbers aren't precisely the same, and we end up forming a few more B's in the third dice roll. We lose one of those B's in the fourth dice roll. And now we're evenly split between A's and B's. To the fifth dice roll, again, B's to A's, A's, where is one A converting to B? And some of that happens on each dice roll. So now let's scroll down and look at what happened. We started out with all A's and no B's. After that first dice roll, we have a decent number of each. And what's going on? We have the number of A's bouncing around up and down, number of B's also bouncing around up and down. But they seem to have come to a leveling point. And intuitively, that should make sense. Our ultimate rules are it's about as easy to turn from an A to a B as it is to turn from a B to an A. So there's balance there, and we find that balance here in the end in our graph. So now let's do something that's not quite as evenly balanced. Let's make one of these processes easier than the other. So I'm going to say A going to B, my forward reaction, happens if I roll a 1 or 2 or a 3. I'm making this pretty easy, but I'm going to make going backwards a little harder. In order for a B to go back to A, it has to roll a 6. So once again, I'm going to reset the room and everyone's going to start as A's. On the first roll, any A that rolls a 1, a 2, or a 3 gets to convert to being a B. So we get lots of A to B conversion. On the second dice roll, let's see what's happening here. We're getting more A to B conversion. It's not until the third dice roll in this case that we get a B that's been formed rolling a 6 and converting back to an A, even while we're also getting more A's converting over to being B's. After the third dice roll, we have a lot of B's. Remember, it was really easy to form them. Only a few A's left. And that situation persists as we keep going. But notice in every turn, we typically have some A's turning into B's, some B's turning into A's. And if we graph this in the end, here's what we have. We made it really easy for A's to turn into B's, so that happens pretty quickly. But after just a few rolls, we settle down and the number of B's has sort of plateaued out, and so has the number of A's. So what's going on here mathematically? How do we describe this in terms of our equilibrium constants? The equilibrium constants really arise out of probabilistic rules like what we just simulated. Let's go back to the evenly matched simulation. An A could turn into a B with a roll of a 1 or a 2. Another way to represent this is to say the rate of the forward reaction, how many molecules will react on each roll, is the following. The rate of the forward reaction, each roll, a third of the A's on average will convert to being B's. Now, in that first reaction where we could go both ways, we made it just as easy for B's to turn back into A's. If a B rolls a 5 or a 6, it turns backwards. So the rate of this reverse reaction is also 1/3 the number, in this case, of B's. So what happened by the end when our quantities of each plateaued out? At the end, we reached an equilibrium state, and this is really the definition of equilibrium, that the rate of the forward reaction is equal to the rate of the reverse reaction. And we can take the values that we have from up here. The forward reaction, 1/3 of the A's convert over. Reverse reaction, 1/3 of the B's convert back. So if the forward rate is equal to the reverse rate, if we're at equilibrium, we can say what's true about the concentrations at that point. 1/3 the concentration of A would be equal to 1/3 the concentration of B. And now you notice we're talking just in terms of concentrations. And if you're thinking about this in terms of the equilibrium constant, you remember that's products over reactants, in this case B over A. So I could rearrange this equation to solve for B over A. That is K, our equilibrium constant. B over A, I divide by A, I divide by 1/3. So B over A ends up being equal to 1/3 over 1/3, or 1. The ratio at equilibrium of products to reactants is 1:1. And if you remember the graph from this reaction, they settled down to about the same value. They were bouncing around a little bit, but that's where they settled down. Now let's look at the second reaction. This was where we made it easier for A to turn into B. So we made the rate of the forward reaction greater. Half the time we'd expect an A to turn into a B. So the rate of the forward reaction, how many do we expect to convert on each roll? That's half the number of A's. We made the reverse reaction harder. You had to roll a 6. So now the rate of the reverse reaction, the number we expect to switch back, is 1/6 the number of B's that we have. And if you remember, we ended up with lots of B's in this reaction. So at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. Any converting one way are roughly balanced out by those converting the other way. So now we have 1/2 the number of A's, concentration of A's, equals 1/6 the concentration of B's at equilibrium. Again, we can solve for our equilibrium constant, B over A. So in this case, I'll divide by A. That'll cancel this A out. I'll divide both sides by 1/6. So B over A is going to be 1/2 over 1/6, or 3. And that's exactly what we saw in the graph. We ended up with 3 times as many A's in the end as we had, 3 times as many B's as A's. That fell out of the rules of probability. That's really where these equilibrium constants come from at the bottom, the probabilities of forward and reverse reactions. The really amazing thing about this is that this system also helps to illustrate why entropy, why increasing disorder is something we should expect to see in chemical processes. So I'm going to go all the way back to that first simulation to show you why this is connected to entropy. Remember that first simulation where we could only go from A to B, and they didn't settle down. We expect A to trend down to 0. We expect B to trend up to everything's converted. Well, how could we describe this in terms of disorder? Where are we ordered and disordered? Well, we start off in what we could consider a very ordered state. Everything is A. After just a couple of rolls, though, we've gone to a mixed up state. We have this chaotic mixture of A's and B's after just a couple of rolls. But then what happens as we keep going? As we keep converting A's to B's, we end up in the end with a situation where we don't have a mixed up jumble of everything. We're back to just having one type of thing, and we've gone back to more order. Well, this is a problem. This breaks the second law of thermodynamics, And we can't break the second law of thermodynamics. We can't go from disorder spontaneously to order. That should never happen. So what does this mean? This means that our simulation, where we only allow A to go to B, can't be a simulation that accurately describes the universe. In order to accurately describe the universe, we have to allow both forward and reverse processes to happen. Then what happens? So here's our second simulation. We start out with an ordered situation. Everything's A, nothing's B, nice and neat and organized. And after just a couple of rolls, we've gotten to our disordered state, our mixed up jumble of A's and B's. And we're not ever going to go back from that. So by allowing for the reverse process, we've created a simulation that now fits with the second law of thermodynamics, where disorder is going to increase as we go along. So this simulation is illustrating a couple of different things. One is this idea, the term is dynamic equilibrium, that even as we settle down to a steady state concentration, the concentration of A, yeah, it's going to fluctuate a little bit, but it's leveled out. Same thing with the concentration of B. But we saw that because we're still following the same rules, there's constantly A's turning into B's, B's turning into A's. It's not a still dead system. It's very much alive, even though the overall concentrations are not really changing. The other thing that this is illustrating, and this is at the core of the idea of entropy, is that we have a system where every process is reversible on the individual level. And in those simulations, we saw A's turning to B's, back to A's, over to B's again. Every move can, in principle, be reversed, particularly when we look at the individual molecular level. But when we look at the rules applied to the system as a whole, we find that for the entire system, the macroscopic view, the big picture view, we have an irreversible process. If we kept rolling, the odds that we would go back to having all A's, go back to having that ordered system again, or go to having all B's are infinitesimally small. And that's just for the system of 20 particles. For a real system with billions and trillions in Avogadro's number, 10 to the 23rd of particles, the odds of that happening are even smaller. So entropy is really describing that the rules of probability are going to take us to more and more disorder in our dynamic systems at equilibrium.